Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're continuing along with my LTAM course and beginning the content of Chapter 5. Chapter 5 covers annuities. This chapter will be broken down into two parts. This part will cover the basics of annuities, and then the second part will cover some of the more advanced formulas you need to know and more advanced concepts. And similarly, the homework problems will be broken down. Unfortunately, there actually aren't that many problems on the SOA problem list. I was thinking of coming up with a few supplemental ones. The ones I immediately had in mind just didn't fit quite right. They were either going to be too simple or too challenging. I may come up with a few more, depending on what I can come up with. But either way, those few problems that there are also divided into two parts. So after this video, I'll recommend the list of problems that will be solvable with the techniques of this section. And then after the second part, I'll name those problems that can be solvable with the more advanced techniques in the second part of Chapter 5. So, yet again, I'm introducing the notation by showing you what's here in the table. You should be familiar with this by now. Don't worry, this is the last time that I'll show you this same exact table excerpt. But just going through. For annuities, we're going to be focusing entirely on the A double dot stuff. So A double dot X, that is the expected present value of an annuity that pays one of whatever currency you have, pays 1 at the start of each year, assuming that the X-year-old is still alive at the start of the year. Now, you might remember from exam FM that a double dot above the A means payable at the start of the year. Same idea here. Obviously, the older you get, the less valuable these annuities are going to be. Let's see, we covered the big A stuff in Chapter 4. The two columns here, A double dot X colon angle 10 and A double dot X colon angle 20, these two. These correspond to the expected present value of an annuity with a 10-year or 20-year maximum. In general, A double dot X colon angle N means payments stop after N years. This is in contrast to big A X colon angle 10, where it's not that the agreement expires then, it's that you automatically get the payment whether you're still alive or not. That's for big A. Here, with little a double dot, it's that the payments just stop. One way that you could imagine this, that it can relate little a double dot and big A of X colon angle 10, is if you had reason to believe that some cataclysmic event was going to kill everybody in 10 or 20 years. Then, it wouldn't matter what the normal mortality table says. Payments conditioned on the person still being alive would stop after the cataclysm. And, assuming that there was an insurance company to make a payout post-cataclysm, so maybe a cataclysmic event isn't exactly the best way of doing it, or best way of thinking about it. Should clarify, I'm not going to actually conduct or instigate a cataclysmic event. No. But perhaps cataclysmic event isn't the best way of thinking about it, because for big A, you'd still need some institution to be able to make the payout, but assuming that they could, then yes, they would have to make the payout after 10 years. So that's one way of thinking about, if for whatever reason you knew that, regardless of whatever the mortality table said, you knew that this person was not going to survive more than 10 years. then you could just use x colon angle 10 for both the annuity and the insurance situations. Anyway, so with that in mind, you'll notice, obviously, a double dot x colon angle 10 cannot be greater than 10. A double dot x colon angle 20 cannot be greater than 20. Notice the reason why these are noticeably less than 10 and 20 is because even if we remove mortality, if you do the math, assuming 5% interest, which this table presumes 5% interest, if you do the math, even if you make 10 or 20 annual payments, you'll get something only a little bit bigger than these numbers. And again, just worth mentioning, the older you get, the less valuable the annuities are. And also, of course, if there's a greater restriction or a stricter restriction on how many payments you can have, obviously that's going to decrease the value of an annuity. So, a double dot x is worth more than a double dot x colon angle anything. A double dot x colon angle 10 is going to be worth less than a double dot x colon angle 20 because there are an additional n possible payments that are included in here that aren't included in here. Lastly, I'll review these endowment columns because we'll be using them quite a bit. This just means expected present value of an endowment agreement. That means it'll pay 1 if you survive a certain number of years. So that's equal to the probability of survival times however many years of discount you need. So if you get confused about any of that notation, just return back to this part of the presentation. And so here's kind of your one stop for all the annuity notation. All right. So as an example, suppose you have a term annuity. Suppose a 40-year-old purchases a 25-year term annuity of $1,000 a year. You can ask, how much is this annuity worth? Using your standard assumptions. So a term annuity, if it were a 10 or 20-year term annuity, you could just look up a double dot x colon angle 10 or a double dot x colon angle 20. And of course, so I said it was a 40-year-old, so here you actually have to go deeper down into the table than what I have up here. But if you look at the full tables, then you'll have the full values. All right. So if I wanted something like this, right? A double dot x, a double dot 40 colon angle 25. I have to multiply by 1,000 because this isn't paying 1 per year; it's paying 1,000 per year. And the way I can construct a term annuity is I just say it's the full 40 years minus anything starting at age 65, right? Because that way I get just those 20-year payments. But of course, I can't just plug in a double dot 65. That already assumes that the person lives to be 65, which we can't necessarily assume, and doesn't account for 25 years of discount. So we need the endowment column. We need the endowment figure. And if we had, and there are a couple ways of getting 25E40. You could do L65 over L40 to get the probability of survival, and then divide by 1.05 to the 25. Or, I have here, you could take 20E40 times 5E45. And you can confirm these figures from the tables. If you want to pause and double check the tables, make sure that you get these figures again, or that you look them up and that the table still says those. And yeah, you can do that and confirm that is the calculation, and you get the expected value here. So again, when you have a term annuity, you can just say, I account for everything starting from right now. I subtract out everything past when the term ends. And to do that, you just look at the value of that later annuity, and you have to account for the appropriate time delay, which you always handle with an endowment figure. So that's what happens if there's some time before the annuity, there's some time until the annuity ends. What if there's some time until the annuity starts? It's called a deferred annuity. We use the same deferral notation for annuities as we have with survival probabilities and for insurance. To defer by U years, we just have the U vertical bar, A double dot X colon angle A. So this would mean that the annuity starts when the person is X plus U years old. The person is currently X years old. It's going to start when the person is X plus U years old, and end when the person is X plus N plus U years old, right? It's going to last for these N years, or until the person dies, whichever comes first. All right. Note, we do have this relationship that what I can say is, all right, so if the annuity doesn't do anything for a while and then starts some amount of time later, right, then I would have to multiply by the U-year endowment figure. I'll say, yeah, doesn't do anything yet, but in U years, the person will be X plus U years old, assuming the person survives. And so I can pretend that it's an annuity that starts that much later, but then I have to subtract out everything past the end of the term. So U plus N EX, A double dot X plus U plus N. Again, you start with some amount, right? So you say if it begins at some later date and ends at some even later date, I can say that that is a delayed annuity minus an even further delayed annuity. So suppose a 20-year-old purchases an annuity that will pay $1,000 per year beginning on her 35th birthday and ending just before her 55th as long as she's still alive. How much is this annuity worth? Use the basic assumptions. So what you're trying to find, that this expected value is A double dot 20 colon angle 20 deferred 15 years. And so we can say that's going to be 15E20 A double dot 35, right? That waits until it's about to begin, minus everything after the end of the annuity. 35E20 A double dot 55. And to crunch these numbers in, this 18.9728 is A double dot 35 from the table. You can double check that yourself if you want. A double dot 55 is going to be 16.0599. And to get these endowment figures, I have to multiply some component endowments, right? Because, well, okay, so there are a couple ways you could do it. You could just say, for this one, for 15E20, you could do L35 over L20 times 1.05 to the negative 15. And if that's how you like to do it, yeah, that'll work. Something else you could do is you could say, well, delaying 15 years is the same as delaying 5 years and then 10, or 10 years and then 5. And the reason we might want to do that is because we have a 5 and 10 year delay built in. We also have a 20-year delay built in, but we obviously wouldn't use that when you're only delaying 15 years. So I'd say I have to delay 5 years, sorry, I have to delay 10 years from age 20, and then 5 years from age 30. Or I could have done 5 years from age 20, and then 10 years from age 25. And then for this, I have 5 years from age 20, 10 years from age 20, 5 years from age 30, and then 20 years delayed from age 35. So I crunch my numbers and I get an expected value of 6.2371. Now, because I picked a 20-year term, and our original table has stuff with 20-year terms in it, might there be some way of just saying, well, if I knew what it would be worth, if I could look up A:35 : 20, can't I just do that and do a 15-year delay on that? And the answer is, absolutely you can. In fact, it's a little faster to do that. If you do it this way, then you just get these same figures for the 15-year delay starting at age 20. You multiply by the 13.0240 that A:35 : 20 gets you, and then you get 6.2370. So of these, they're identical to within a rounding error in the fifth significant figure. All right. So with all this discussion about deferred annuities and term annuities, and you realize, well, wait a minute, that's piecewise. I'm kind of turning the annuity off and turning it back on. You might make the mental connection between that and the Frakennuities that I was talking about in Chapter 4. And yeah, that's where I'm going with this. Welcome to Frakennuities, where you just Frankenstein together a couple of different annuity policies. And so we've kind of been doing that. I've been saying, well, this one begins later and then ends. That's the same as saying it was the whole life and then I turn it off afterward. So whenever your benefits package is piecewise defined, right, it doesn't have to be perfectly binary, 1 and then 0. Whenever your benefits package is piecewise defined, you can break it down to a Frakennuity. So an annuity given to a 30-year-old pays out $100 a year for 10 years, $200 a year for the following 20 years, and $50 per year for the rest of the person's life. And I should mention, this is 100 a year for 10 years as long as the person is alive, and 200 a year for the next 20 years as long as the person is alive. I should have specified that. Later on, we'll talk about guaranteed annuities, where these 10 and 20 years would happen regardless of whether the person was alive or not. That is not what I meant here. I apologize for any ambiguity. But here, I mean, if this is in force as long as the person is still alive at the beginning of the year. So, now that we've clarified that, under that definition, how much is this annuity worth? Assuming the standard assumptions, well, if it's 100 to start, and the person's 30 years old, if it were just that constant 100, then it would be 100 A:30. After 10 years, it goes up to 200, so you add an additional 100. But by that point, the person's going to be 40 years old, and it only kicks in if the person has survived long enough. And then it drops from 200 down to 50, so that's minus 150. And that's 30 years delayed from the start, right? So from currently. So you can say it's 100 A:30 plus 100 10E30 times A:40 minus 150 30E30 times A:60. Notice that to get 30E30, you could either do L60 over L30 times 1.05 to the negative 30, or you could do 20E30 times 10E50, or 10E30 times 20E40. Just break it down, break that 30-year delay down into a 10 and a 20-year delay in either order. Just be consistent about it, and remember, after the first delay, how old is the person? Crunch your numbers, looking at stuff from the table, and you get 2565. 2565.84. Alright. So there are some important recurrence relations for annuities, much like there were for insurance. So what if you want a 1-year recursion? What if you want to compare a double dot x to a double dot x plus 1? Well, I can think of a double dot x as you get the first payment right away, right? Because it's only conditioned on your surviving to that beginning of the year, which obviously has to happen, right? You presume that you're still alive, still in force, or the policy is still in force. Then, if you survive, you'll have a double dot x plus 1, but that has to be discounted by 1 year of interest. So you get a double dot x equals 1 plus px over 1 plus I, a double dot x plus 1. And if you have a multi-year recursion, you get a double dot x equals a double dot x colon angle n. Right? That's just the first n years, plus nex, a double dot x plus n, right? Standard time delay for n years times whatever happens after those n years. On the LTAM itself, they may make you calculate a double dot x colon angle n by hand as long as n is no more than 3. Once it gets to be more than 3, that's usually too much for them to expect you to calculate by hand, unless there's some obvious shortcut somewhere in there. So, for example, if you had constant force of mortality, so that the survival probability is exponential, and level payments, so that survival probability is exponential, and then, or exponential or geometric if you think about it in a discrete case, and the payments, the present value of payments, are also geometric. Then present expected value, once you account for mortality, it would be also geometric. You just multiply the ratios by each other. And you should know how to sum a geometric series with an arbitrarily large number of terms. They could ask about that. I can't think of any cases off the top of my head where they did, but it would be perfectly reasonable for them to ask that. Alright, so we can actually use some recursion to extend beyond what the table tells us. A little bit. Not very much, but just a little. The table gives us values for people up to age 100. What if we wanted to know the value of annuity for a 101-year-old? I could use the 100-year-old line. Notice the 100-year-old line does have Q sub 100. It does tell you the probability that a 100-year-old dies before turning 101. And using that, we should be able to figure out the value of a $1 a year annuity for a 101-year-old. All these annuities are, if I don't specify otherwise, they are whole life annuities payable at the start of the year, and conditioned on the person surviving only to the start of the year. If I don't specify otherwise, that's what I mean. And the reason why, the reason why I assume that is because it's in such common practice. The reason why it's in common practice is because that makes the most sense for premium payments. A person pays the premium for a life insurance policy every year, and we'll get into that in more detail in Chapter 6, which is all about analyzing premium payments and calculating what premium you should be charging. But I figured I'd give that brief digression for now, just so that you see where I'm going with this. Anyway, so if we know everything for the 100-year-old line, we should be able to use 1-year recursion for the value of an annuity for a 101-year-old. And that's what we do. We use our formula. We say a double dot 100 equals 1 plus P100 over 1.05 times a double dot 101. Algebra happens, and we get a double dot 101 is 2.5357. Where this you find directly in the table. If you look up a double dot 100, you should find this. Here, this is the Q value that you look up in the table, and you just do 1 minus that to get the P value. And you don't have to do it with only a 1-year recursion. What if I wanted to calculate that same value for a 10-year recursion? I could use a 91-year-old line. So I could say A double dot 91 equals A double dot 91 colon angle 10 plus 10E91 times A double dot 101. We find A double dot 91, we find A double dot 91 colon angle 10, and we find 10E91 right there on the 91 line. Crunch our numbers, and we get A double dot 101 equals 2.5359. So it's slightly different from what we had before in like the 5th significant figure. Yeah, we can expect some rounding. In fact, this this 10E91 is only reported to 4 significant figures, so it's no surprise if there's a difference in the 5th significant figure. But the important thing is we got pretty much the same answer, so at least it's consistent. And those are just examples of how to use these recursions. In theory, you could use something like this, including the A double dot x colon angle 20 line, to extrapolate and get everything up through survival probabilities to age 120. Because the 100-year-old line does have an A double dot x colon angle 20. Obviously, the data on that would be, so any relative errors on that could be significant once you get into survival probabilities to age 120, because throughout human history, there's only been one verifiably recorded by modern standards of verification, one verifiable recorded case of a person living to at least age 120. And there's even a theory that the person did not actually live that long, and in a case of identity theft, the actual person, there's a theory that the actual person passed away in her 30s, and that her daughter assumed her identity in order to avoid paying inheritance tax. Though there's no concrete evidence to support that conspiracy theory. Some people have just calculated based on estimates of how likely people would be to implement that. And that the official records show that it was the daughter who passed away at that date. And comparing that to the likelihood of someone surviving that long, people have tried to argue that it's highly unlikely, but that she actually lived that long. But there's no concrete evidence to support the conspiracy theory. Anyway, so all that aside, what this means is however they're inferring survival probabilities to age 120, there would be some uncertainty there, which is probably why the table doesn't go past 100, just because that's where you start getting really small sample sizes. But just as an algebra exercise, yeah, we can do that. So, as you may remember from exam FM, there's this rather confusing notation or confusing terminology about immediate annuities versus annuities due. You would think that an immediate annuity is one that pays immediately, and that an annuity due pays at the end of the year, so that your payment is due, you're owed something. In reality, for reasons I do not fully understand, the terminology is exactly the opposite. That an immediate annuity means payments at the end of the year, and an annuity due is payments at the start of the year. A double dot X means payments is at the start of the year. That's an annuity due. AX means payments is at the end of the year. Now, they're both conditioned on the person still being alive. For A double dot X, the condition is that the person is alive at the start of the year. And there's a question, does AX without the double dots, does that mean the condition is the person has to still be alive at the start of the year, so that it's at least the same condition, or at the end of the year, so that you still have to be alive for payment? The answer is the latter of those two. Still alive at the end of the year. Now, clearly, annuity immediate, because payment is somewhat delayed, annuity immediate is worth a bit less. Both because payment is delayed and because there's a chance that you won't survive to the end of that year and you might not get payment. And the question is, okay, so A double dot X is worth more. How much more? For a whole life annuity, the only difference is that at the very beginning of the year, or at the very beginning of the term, you immediately got one. As the calendar flips over, year after year after year, in either case, you'll get one, as long as you're still alive. And then whenever you die, that's when the payments stop. So we just say A double dot X equals AX plus 1 for the start of the year. If it's a term annuity, A double dot X colon angle N, so that's for the most part the same as AX colon angle N, but again, there's that payment of 1 at the beginning, and then suppose you survive for those N years. Because you still need N payments, since your first payment was at the beginning of the first year, you don't get one at the end of the nth year. Right? That would be double counting that nth year. You'd be paid at the beginning and the end. Whereas when payments at the end of the year, you do get paid for that. So if you survive the n years, then AX colon angle N receives one additional payment worth NEX that wasn't there in the A double dot case. So you get A double dot X colon angle N equals AX colon angle N plus 1 for the beginning of the year, minus NEX for value of 1 times the probability that you survive, divided by n years of interest. So for example, suppose a 30-year-old receives an annuity of $1,000 per year at the end of the year until age 65, after which he will receive $600 a year at the end of the year as long as he lives. How much is this annuity worth? So we notice this is a Frakennuity, and it's also end of year. So we want to use both the Frakennuity formulas and the annuity immediate formulas. We'll point out that, so you could say it's you could say it's 1,000 minus 400 times a deferred annuity, or you could say it's 600 plus 400 times a term annuity. And I would like to do it this way with the term annuity, just because we have a nice formula for term annuities. So, assuming the standard ultimate life table can be used, right, we can just look up our formulas, right? We'll say A30 equals A double dot 30 minus 1. And A double dot 30 colon angle 35 equals A double dot 30 colon angle 35 minus 1 plus 35E30. We look up all our numbers. So 35E30, right, we can't just look up. We either do L65 over L30 and divide that by 1 plus I to the 35, or we do something like 20E30 times 10E50 times 5E60, or something like that. We do that to get our crunch our numbers and get A 30 colon angle 35. Right? This is just algebra. Again, we need, so Frakennuity formula here, conversion between annuities due and annuities immediate here and here. And then we're just plugging in our numbers and getting the answer that is worth about 17,520.32. So, a couple more ideas over time. That is to say, they increase by the same amount from year to year to year, or decrease by the same amount from year to year to year. We'll have to introduce increasing annuity notation. If you see IA double dot, that means the annuity pays 1 now, 2 1 year from now, 3 2 years from now, etc., until the X-year-old dies. And decreasing annuities can be viewed as Frakennuities of a level payment annuity minus an increasing annuity. And if you can't quite see that, I'm about to show you how. So, let Z be the present value random variable of an annuity to an X-year-old that pays 20 now, 19 a year from now, 18 2 years from now, etc., until payments hit 10, at which point they level off. Assuming the standard table can be used and everything. Sorry, we don't assume that. We don't assume that. We say, I forgot what I had said about this problem, but yeah, for this problem, we'll say A double dot X equals 18, A double dot X colon angle 10 equals 8, and IA double dot X colon angle 10 equals 40. With that, find the expected value of Z. And the trick is how to Frakennuity this into a combination of what we have. Well, I can break this down into the first 10 years, from when it starts at 20 and decreases down to 11. Notice, when it decreases down to 10, that's actually going to be the 11th year. So the first 10 years end with the 11th payment. And then I can think about everything after those 10 years where the payments are just 10, 10, 10, 10, 10. So, after the first 10 years, it's just going to be payment of 10 times A double dot X minus A double dot X colon angle 10, right? A double dot X minus everything from the first 10 years is going to get me everything after those 10 years. So I crunch the numbers, I get 100. Just the first 10 years, what I'll point out is to go 20, 19, 18, 17, etc. That's the same as a constant 21 minus something that goes 1, 2, 3, 4, 5. So I can say it's 21 A double dot X colon angle 10 minus IA X colon angle 10. I crunch the numbers in. I get total expected present value is 100 from everything past the first 10 years, plus 128 from just the first 10 years. Get a value of 228. And so we can talk about guaranteed annuities. That's when payment is guaranteed for a period of time regardless of whether or not the recipient is still alive. So, suppose an annuity pays $1,000 per year as long as a given 50-year-old is alive for a minimum of 10 years. How much is this annuity worth? Assuming the standard ultimate life table can be used. We'll say expectation of Z is equal to 1,000 times, now here, it should be A double dot 50 colon angle 10 with a line over it. And unfortunately, apparently this isn't formatted properly. There should be 2 overlines here. And just notice now that it was formatting badly. So it should be an overline above the angle. Right? in general, a line over two conditions means it's whichever of those two happens second. So you've got the 10 years and the 50-year-old. Again, this should be an angle here. Otherwise, this means something else. And we'll talk about what that means in Chapter 9. But what we can say is we can break it down into the first 10 years, which is just 1000 A double dot colon angle 10, plus everything after those 10 years. For 1000 A double dot angle 10, we can just use the geometric series formula. And for everything after those 10 years, we can just crunch the numbers normally, looking them up from the table. So we crunch all our numbers, arithmetic happens, and we get 17,691. Finally, I said there were two ways of the payments increasing or decreasing. You could have geometrically increasing annuities. You almost never have geometrically decreasing annuities. Often, payments will increase over time to reflect the increasing cost of living, right? If this annuity is, let's say, part of a pension payment, then you'd have to, if you retire at age 65 and there's a chance you could live to like age 110, 115, maybe even 120, then you're talking about upwards of 40 years of interest. So often payments will increase over time. And the increase in cost of living should be roughly the same as the inflation rate, which should consistently be lower than the interest rate. And for that, you can modify the interest rate, right? If you remember from back in exam FM, when you had both interest and inflation, if your face value is multiplying by 1 plus j, if j is the inflation rate, but the interest rate means you have to divide by 1 plus I, that means that the real value multiplies by 1 plus j over 1 plus I. Which means it gets divided by 1 plus I over 1 plus j. Right, so that this is kind of like a modified growth rate, and so the interest rate is just that growth rate minus 1. So, suppose a 3-year annuity. Suppose there's a 3-year annuity for a 60-year-old. It pays $1,000 immediately and increases each year by 2%. Again, assume it's a whole life annuity. How much is this annuity worth? So, it would be 1,000 plus 1020 over 1.05 P60 plus 1,000 times 1.02 over 1.05 times 2 P60. Notice we would never end up looking up A double dot 60 or 61 or 62 or 63. We wouldn't be looking that up because we essentially have to modify the interest rates, and all of the values in the table that deal with finance are only valid with an unmodified interest rate. So we just have to crunch this out manually. And we'll get E of Z is, crunch it out, and we get 2905. Anyway, that's it for part 1 of chapter 5. Now, the SOA problem set list for chapter 5. Some of those relate to stuff in part 1, and some relate to stuff in part 2. The problems you should be capable of working on now are 4.22. Remember how I said 4.22 related to stuff in terms of stuff that would be covered here? Yeah, that had increasing annuities in it. It actually relates to a continuous increasing annuity, but that shouldn't be anything you can't figure out how to handle. So 4.22, as well as 5.1, 5.4, 5.9, 5.10, and 5.11. Again, your homework assignment at this point is to do problems 4.22, 5.1, 5.4, 5.9, 5.10, and 5.11. I'll be posting worked solutions to those problems shortly. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. Until next time, this is Dr. Nighttime wishing you a good night.